So my name is Rob Pike. I work at Google. I used to be a physicist, which makes me feel kind of funny to be here. I actually really enjoyed hearing about some quantum mechanics. When I was at Bell Labs, I was actually, for a while, head of the quantum computing group there. So it's kind of interesting to see that again. And I feel kind of like an interloper.
Right on. Sorry to interrupt you. You need to turn your mic on.
Nobody told me that part.
Keep on going.
I feel like an interloper because I'm not really...
This one's not this one. You get this one.
No?
So you have to say I'm an interloper again.
I'm an interloper.
Okay.
There we go.
Right on.
I'm an interloper because I don't really consider myself a language designer. I think of myself as a physicist, graphics guy. I designed an operating system because I wanted to do better graphics. And as a result, I also ended up kind of doing language work because I didn't like the way the languages we had were solving their problems. And so I'm coming to you today entirely as a pragmatist, not as a language expert. And so take it easy on me. I'm going to give you a brief history of two programming languages I've been involved in the design of. One, I was kind of the principal designer. The other, I was a co-designer. One of them is invisibly and implicitly parallel, and the other one is explicitly concurrent. And both of them have been used to do real stuff. The first one, most of you probably never heard of, but was very important for a while at Google. It's a language called Sawzall, and it was a big data processing language. When I got to Google in 2002, I wasn't doing quantum computing anymore, and I got asked to fix the log analysis problem we had there. We were getting things like web query logs coming in at a literally exponential rate at the time. And the analysis was written in Python and was getting close to 1 day per day. And at some point, it was clear that wasn't going to last, and we had to be able to generate the bills. So Sean Quinlan and I were tasked with doing something about this, and we designed a system called Sawmill, which is the entire system. It managed the data flow throughout all the servers and all that. And we needed to design something because nothing existed at this scale. Databases are hopeless at this scale. We're talking massive, massive injection rates. You can't do queries while you're generating that much data. Even if you could build a database big enough to hold that much data, the incremental changes would kill you. So we proposed something totally different, which was kind of a distributed database engine that handled simple counters, basically, counted how many times events occurred in a distributed setup, and gathered all the data from all of the servers, generated these counters, and did continuous updates. So at any moment, you could go to the system and say, how many users are talking about this page from China today or whatever. And to program these little counters, we designed this little kind of parallel awk. It's like awk. It doesn't look like awk, but it's the same basic idea, which is just a simple expression-y language with some statements in it, but lets you talk about how to analyze the data line by line. Now, that was the theory. In practice, what happened was we had a year to design this, but we ran out of days, and we started not being able to generate bills anymore. And so we launched 3 months early. And maybe the first distributed system and or language and or production thing that actually launched 3 months ahead of schedule. As a result, some things got dropped on the floor that I regret, but there's reality. And particularly the continuous engine didn't happen. But the language that we designed and mostly implemented by then to run it did exist, and it turned out to make a lot of sense. We just had to adapt it to a more batch environment. And at the time, Jeff Dean and Sanjay Gemwat were just getting MapReduce working to develop the web indexing pipeline. And we were probably the second big user of that. We started running Sawzall jobs as MapReduces. This was in mid-2003. And the language was still a really good fit for this, even though it was a batch rather than an interactive thing or a dynamic thing. And the big news from the people who actually care about this stuff was that to process a day's logs went from 24 hours to about 2 minutes. And that was considered progress. The language is very, very simple. It just looks like it's not typeless, but it looks almost like a scripting language on the page. It was strongly typed, had a very uninteresting general programming model with one wrinkle I'll talk about. What was interesting about it was the query programming model, which was the thing that was used to actually make it work in a distributed environment. And that was these things called tables, which you can think of as just being sort of generalized associative arrays. So here's an example of a little Sawzall declaration in use. There's a table called queries by country, which is declared to be a sum table. Sum is a keyword. Country is just an identifier that tells you what this index represents. So it's a sum of strings that represent countries, and you get ints out of them. So in other words, it's just counting something indexed by country, right? And then inside your Sawzall program, when you wanted to add something to that table, you did an emit statement, which was an index expression and a value. And the index expression identified a table and an index. And the index, that could be multidimensional, but they were also totally dynamic. So it was just like I said, an associative array of arbitrary types inside there. And so you could build fairly complex examples, and I'll show you some in a minute. The table types themselves were interesting. There was about a dozen of them. Initially we launched, I think, with these ones. There may have been some I've forgotten. But a sum table counted, just said, if you add 2 to the table or 1 to the table, it just, that index entry you got, that added to the value. There was a quantile, which does what it sounds like. You could do the top, like 10%, 20%, 30%, break up the population. There was a top table, which counted the, say, 10 most highly weighted of a certain thing. Both the quantile and the top tables had to be approximate. There were some interesting algorithms for the approximation because you can't do those algorithms efficiently otherwise. And there's a histogram, and there's some others that came later that were more complicated. But the basic idea was in 2 or 3 lines of code, you could specify an interesting data question and get the answer by running a Sawzall job in production. So what the execution model was very unusual. You actually wrote your program. This is where the sort of awk idea came in. Your Sawzall program described how to think about exactly one record. So if you think of your log file as just a lot of records, a single log entry went into your Sawzall program, and all the table definitions and procedural code that generated the values caused the updating of those tables appropriate to that exact record. You couldn't ask what the record before was or the record after, just the one you were looking at. And you could run this because it was so localized. You could run it fantastically parallel, 5 or 10,000 machines at once. In fact, we did it on multiple cores simultaneously as well. And you could therefore run tremendously parallel. That was done in the map phase of the MapReduce in the later design, the one that launched. And then in the reduce phase of the MapReduce, you gathered all these streams of data coming in from all the servers, and you collated. So if you had counts, that was easy. You just add the buckets. But for quantile and histogram, top tables, that was a more subtle algorithm. But it still worked in parallel, and there was fairly clever stuff to make it happen. And so, as I said, you could throw thousands of machines at a problem that used to be hard to solve on one and get the answers in a matter of sometimes literally seconds when it used to be a day or more. The output of this was then dumped to a file which you could use any way you like. Further processing, you could run another Sawzall job with that as the input. You could mix it with other tables, make things happen, or you could inject it into a database if you'd reduced it enough that it would fit. Now, the implementation worked by having the Sawmill system, the system at large, ran your jobs for you, gathered the data, pulled it back to the Sawzall servers, crunched the data, and did the work. Inside the implementation of the language proper, there was a very simple interpreter. We wrote a very straightforward interpreter. It was Robert Grieser and myself. We did just the straightforward stuff, and then we benchmarked it, and it was 4 times faster than Python. I still don't understand how that's possible because that tells me much more about Python than about our coding skills. But it was a reasonable implementation. We didn't try to be slow. But because it was statically typed, we probably got a big advantage there because we could generate the correct add-op instead of having to figure out every time, yeah, this really is a 3. Later, Regis Crillier did an on-the-fly compiler that bought another 2x maybe. It was worth it for the scale of the jobs we were running. The most interesting part of the implementation at this stage was probably that there was a custom protocol buffer parser. The language was designed to work on protocol buffers because that's how we store all our data. And you could actually customize the protocol buffer parser for the program that was going to be looking at the protocol buffers. So some of these records might have 10,000 values in them, but you only care about 3 of them. And you could generate a much more efficient protocol buffer parser if you only cared about those 3 values rather than the other 10,000. And that actually made a huge difference in performance, 10x or more. And then one of the really cool things about this was because the computing model was one record and then throw it all away and go to the next record, the garbage collector was a pointer move. You just had to throw the arena away and start again. So it was actually a pretty simple implementation and it worked really well. And being an interpreter, we thought would hurt, but maybe not. It turned out it didn't hurt much at all, at least in the early days, because we were I/O bound. And we could keep all the by I/O bound, I don't mean just networking, but also protocol buffer handling. And it took a few years before the programs got big enough that we needed a better implementation for the language proper. So here's an example. This is a full, complete example that probably doesn't run anymore, but it's from an old paper. And I'm not going to go through it all, but I'll just say that you can see there's a definite at the top for proto. It tells you what the record format is that it's going to be using. And there's a static value, which is just essentially a constant, which is 60. And then this next line, log record query log proto equals input. Input was a pre-declared variable that was reset on every line on every record you reach to be the raw data of that record. And that line doesn't look like it, but that actually parsed the input and turned it into a data structure under the format of the fields of the log record you were interested in. And then there's a table called datum for no good reason, which is triply indexed. It's got a time and an integer latitude and longitude. And then this program computes the location information for the record, and if def-lock says if that succeeds in that calculation, that is, it was an okay, we were able to find a location for it, then we compute some values and emit one entry to the table and put one in there. So it just counts this event occurred in this time interval at this location on the Earth. And 2 minutes later, we could print this graph, which is I hope that shows up. Yeah, you kind of see it. That's an animated GIF running at something like hour resolution, I think it is. And the reason this day was interesting was that was the day there was a big power outage in the east coast of the United States. And what we learned from looking at this diagram, you can actually see it happen if you look for it closely, but what we learned was that the internet is battery backed up. You don't really see much happening there. There is a little tiny darkening, but not much. But the cool thing was this was the kind of thing that was done once before with the old system, but it took days to compute the data. And in this case, it only took a few minutes to put it together. Here's another one. This is actually, I think, more fun. This is a very simple. This is a 2-line program. You just look for queries that contain the word earthquake and count them, and then remember when they happened. And if you look at the bottom here, the resolution of those lines is just, I think, 10 seconds. So we can tell you when the earthquake happened to within a few seconds based on when people said, hey, was there an earthquake? And in fact, if you look at the USGS information for this earthquake, I think we have higher resolution on it than they do. It's pretty cool. And this, of course, means there's all kinds of things you could think about doing. You could ask questions about the data stream, find events that are happening, do what was now called the zeitgeist, which grew out of this work. So it's kind of cool. This little tiny language could let you find things like when the earthquake happened, which was not really expected, but was a really nice result. So in other words, it really got used in production. It still is used a little bit, although it's fading away. It completely changed the game. The profound change in throughput for executing these queries had a huge effect on the business. We started to be able to ask questions about what we could do differently to search quality, to ad generation, interesting experiments in languages by human language analysis and things like that. And not only was there great speed, there was also massive scale. When we wrote the paper, which was a few years ago, I did an analysis. I actually watched one of the clusters that was running nothing but these jobs. And in March 2005, 18 months after the service launched, one cluster alone used 1 CPU century of Sawzall time, processing 2.8 petabytes of input. And I think generated about 10 terabytes as output. It reduced it, but it was still a lot. And it had a huge effect on the business, which was successful and nice. So Sawzall got some stuff right. It was very easy to program, and it was designed to be. It was designed so that people who weren't professional programmers, like product managers or just managers, could write simple programs and ask questions about the data. And they were able to do that, and they did it a lot. And as a result, things happened that were made possible by this. I think the 1 record per query model was a really interesting decision and a really important one to the success of this thing. And the table abstraction was also an interesting way to think about it. It turned out to be a perfect fit for MapReduce. That wasn't the plan, but it worked out really well. So this feels somewhat more familiar to people now, but when we did it, it was kind of a radical thing. What was even more radical was doing a new language for something at Google. I was asked, really, we can do a language? I said, yeah, it's easy. We have tools for this. But to some people, the idea of a new language back then, at least, was really unusual. And so we got this result was a very highly scalable computation and able to handle massive amounts of data. There was one missed opportunity I want to mention, which was we went into the language. I was really happy with this. I thought it was a brilliant idea. I still do, but it was never really used properly. So here's an expression: emit table of f of x gets 1. The question is, what happens if f of x fails for some reason, gets an exception in your terminology? Well, so I didn't want to put exceptions into the language because that makes it harder to use. So instead what we did was, if the equivalent of exception occurred in evaluating f of x, which is very likely if you're talking about a terabyte of data, there's going to be some bad data in there somewhere. Rather than have to check every time whether f of x is okay, we just elide from this particular run of the job, on this one record, all of the computation that depends on that result. We just pretend it didn't happen. And we, by the way, write a log on the side that says this happened. But the idea was you could throw your query at the data, not worry about errors, and if you got less than 1% bad records, you probably had good data. And you didn't have to put exception handling or tricks all over the place. I thought it was a really cool idea. And it didn't work. And the reason it didn't work was not technological, but social. People didn't like the fact that they couldn't tell whether the thing had happened or not. And they wanted to be able to write rules about how the code should be written to do proper billing and so on. And they forced everybody to put in what we call def checks, defined checks, rather than let this automatic elision happen for them. And so as a result, the language in practice was much uglier than it was in the paper or in our examples, and it made me very sad. But I'd like to say that Martin Renard at MIT, shortly thereafter, roughly simultaneously, wrote a paper on failure-oblivious computing when he did something very similar in a C compiler, where the C compiler, for security reasons, ignored bad data and kept running, but didn't let you know something had gone wrong. So other people had the idea as well. What Sawzall got wrong is very important, though. It got a lot wrong. We aimed way too low in terms of the level of the language and how rich it was in its type system and modules and so on, because we thought we were going to be writing 5, 10, maybe 50-line programs tops. And in fact, by the end of the sort of important lifetime of Sawzall, programs were 100 and 200,000 lines long. And you don't want to write 200,000-line awk programs, and you certainly didn't want to write 200,000-line Sawzall programs, but that was the only way you could get this great parallelism. So we just didn't predict well enough how the language would be used, partly because of the original design, which got abandoned when we rolled out the MapReduce version rather than the continuous version, but also partly because we weren't imaginative enough. So it had no modules, no libraries, no namespaces, no encapsulation, no object-oriented code. It was just simple, and it was too simple. Great to get started, not good at scale. And so eventually we had to do something else, and I'm not going to talk about that. But I will say that the computation model that I think it pioneered lives on in the new paradigm, and I'm pretty happy with that. So in conclusion, Sawzall made parallelism trivial even for people who don't think about themselves as parallel experts. In fact, I don't think anyone using Sawzall thought of themselves as a parallel programming expert. Ironically, there's no parallelism visible in the language anywhere, or maybe not ironically. It completely hid it, and yet, honestly, I sometimes think this is probably about as parallel as a language has ever been. And yet there's no parallelism visible, and it worked out great in practice. So the irony here is that it handled data scale superbly through tremendous parallelism and a good computing model, but handled program scale really badly because we didn't predict how big the programs would get. Yes?
Constructs like table were not implemented in the language.
Constructs like table were written in C++ underneath it. See? Yes.
I'm going to talk about the importance of what is not said tomorrow.
Okay.
And maybe it handled parallelism so well because there was no mention of parallelism.
Yes, I think that's right. I think it handled parallelism so well because it wasn't there. But in the next other language, it's not going to be like that for a different reason. So now I'd like to talk about another language that most of you probably have heard of, which is Go, which was done a little later. And Go arose primarily out of a discomfort with C++. I know Bjarne was very polite and didn't complain about other languages, and I don't want to complain about C++. But I do think it's important to understand the problems we were having with it to at least some extent. Like almost everything written at Google, at the time at least, Sawzall was implemented entirely in C++. And that wasn't because it was the right answer for all of those things we were doing. It just happened to be the language that was available, and it was more of a compromise. There were early conversations about what the Google language internally should be. C++ won that. It was a compromise. I don't think anyone was thrilled with it, but the job got done and they moved on. It's a very complex language, and I say that without criticism. It really is a complex language. But some of that complexity, or maybe most of it, is irrelevant to most of the programs that get written in it. And even in these big Google servers we have, I think most of the language doesn't get used. And it feels like if we're only using a subset of the language, why have all that language there? It's not helping. You can also argue that some people use different subsets. That's not my point. I just think it's bigger than we need for a lot of stuff. Not everything, but for a lot. The real issue, though, is scale. C++ doesn't help at scale. Large code bases, we're talking hundreds of millions of lines of code, take forever to build in C++. They don't need to take forever, but they're going to be slow. But in C++, because of the way it does dependency management through header files, without heroic engineering, it's almost infeasible to build. Everybody who has a big C++ shop uses a distributed compute cluster. And there's also this issue that there are many CPUs, both multi-core on your local machine, and of course we're building these distributed things that need to talk to other guys, and this kind of scale is not well represented by the language. Many network connections talking to clients, services, and things like that. So we need this thing that we need better dependency management and some way of dealing with all these cores or concurrency, and C++ doesn't support either very directly, but to be fair, neither does anything else. And so we decided it was time to do something about this. I define software engineering as the maximization of the quality of the software written by your group of programmers. That's my definition of it. And the key point here is our programmers are Googlers. They're not researchers. They're typically fairly young, fresh out of school, probably learn Java, maybe learn C or C++, probably learn Python. They're not capable of understanding a brilliant language, but we want to use them to be able to build good software. And so the language that we give them has to be easy for them to understand and easy to adopt. And the most important part is, in my personal view, is that it needs to support concurrency very, very well. For Google servers, we just need to have concurrency available. This was a very long battle, and it's only fairly recently been won. For the first N years I was at Google, there were key people who believed that threading was a bad idea, that it was very hard to write code that worked well with threads. And the thing is, they were scared by the models they were forced to use rather than by the idea and how it should be made to work. And as a result, they wrote all these workarounds and avoidance mechanisms that generated horrible code that was hard to understand, Node.js, and things like that, that we wanted to be able to move away. No, it doesn't happen at Google, but you get my point. So anyway, we decided it was time for a new language, but we had to do this, we need to make sure we didn't we had to deal with the scale issues and the concurrency right up front. So we decided to build a very procedural, simple, straightforward language, clean and regular, so that people could learn it easily, but then we're going to slip them this thing on the side that they'd never really been comfortable with before, and it had to work well, and that was concurrency. So around late 2007, Robert Griesemer, who I worked with on Sawzall, and Ken Thompson, who I worked with at Unix and UTF-8 and stuff like that, we decided we had to do something. We couldn't handle the load we were taking trying to write software at this scale. So we started to sketch what we wanted. And I want to stress this was not a research language. We didn't claim we were inventing anything brand new. What we were doing was taking the distillation of ideas from lots of languages that we'd used from years of experience in working in various environments and trying to distill down the essence of what it took to build a really good language for the particular problem domain we were working on. And the key feature we were adding that wasn't there before, at least for most people, is this concurrency stuff. And to do that, we took CSP just pretty directly, really, because I'd had experience with it with some precursor languages I'd done at Bell Labs, and put it inside a purely procedural language, not as a library, mind you, but actually built into the language. And it's composed of three pieces: go routines, channels, and the select statement. And I'm not going to go through the full details of all of them, but I'll just wave my hand over them for a minute. So a go routine is a lightweight concurrent function execution, right? Think of it as coroutine or lightweight thread or green thread or whatever you want to call it. We call them go routines because we wanted a name that didn't already have a connotation that people would be confused by. And it's really simple. You just take any function or method invocation, put the keyword go in front of it, and you start running it in the background. Very much like putting an ampersand on the right end of a command line in the shell or something like that. And it just starts at executing concurrently with the current thread of execution. It might be in parallel. It depends on how many cores are active, but it might not be. It doesn't really matter, and that's kind of the point. Stack allocation is completely automatic. You don't see any stack declaration size there, and you cannot blow the stack, really. It grows and shrinks as it needs. The scheduling is handled automatically, and that's really it. So I've just given you coroutines in 3 characters, 2 keywords, a 2-letter keyword and a space. And that's really simple for people to understand. And these things are designed to be really cheap under the covers. We routinely see tens of thousands of them in production binaries running concurrently, and very often have go routines in the millions that have been created, not necessarily all still around. They're designed to be that cheap. And then there's, on top of that, if you have two things that are concurrent, they have to be able to communicate or they can't really coordinate very well. So we add these things called channels, which again come out of later CSP. And it's just a bidirectional typed pipe, like a queue. You say make a chan event, and now you have a channel that can send integers. You can send an integer on one end and pull it out at the other end. The two ends are not always distinct. There's actually situations where you discriminate them, but mostly it's just a value that you can send or receive to. You can pass types through to clean that up, but fundamentally it's just two ends of the same thing. You have to be allocated. When you allocate them, you can, if you want, although we try to discourage it most of the time, you can allocate a buffer size to go with it. If it doesn't have a buffer, then it's pure CSP synchronous channels. Those are much easier to reason about, but tend to be slower. Because with buffering, buffering helps you go faster. And then to glue all this together, there's one construct in the language, which is a new control structure called the select statement, which is really Dijkstra's guarded commands via CSP turned into a switch-like thing. So there's a select keyword, and then multiple cases, each of which is a single communication operator, maybe a send, maybe a receive. And the idea is this whole thing blocks until one of those can proceed. There's various rules about how to deal with what happens if multiple are available and stuff like that. The semantics are very carefully designed after years of playing around in this space, but fundamentally that's all you need to know. There's also a default clause if you don't want to wait. But the key point here is this is the program constructor. If you have Go routines and channels, you can write simple stuff. And a lot of people say, look, Go like channels in my library I built over here. But unless you have the select statement, you don't really have what it takes. Because select is a thing that lets you build the systems up. It's the computation control structure for building concurrent apps inside the address space. It's the only interesting part semantically. The other stuff's trivial semantically. But it's also the only really, really fun part to implement. It's quite interesting to do it well. Remember, with numbers like millions involved, getting it to go fast is interesting. And then there's everything else that makes it a language, right? It's a simple procedural language. It looks a lot like C on the page, although the declarations are more Pascal-like because they're easier to parse. It is statically typed because that matters. It has real closures, honest to God. The interface model is something I considered making the subject of this talk because it's actually pretty interesting. But they're not quite the way you see interfaces in other languages, and it's the main object-oriented part of this programming language. It's pretty cute. Really important part is fundamentally rigorous dependency management. So an equivalent binary to, that takes 45 minutes to build on multiple machines on our clusters in C++ will build in 10 or 15 seconds on my local workstation and Go. Mostly because of the dependency management being better. And it's procedural. Now, people who love concurrent languages complain about this. And I understand their complaint. But if we made it not be procedural, if we made it be a fancier language that had purely applicative semantics, was purely functional, it wouldn't succeed with our target audience. We had to give them a language they could pick up and understand quickly. And so it had to be procedural. What's nice about it is that from experience before and in practice now we know again, concurrency is actually a really nice fit for a procedural language. You can put it in and it works really, really well. The issue, of course, is you can be type safe, but now you're worried about data races and memory safety. And people complain legitimately that Go can have data races. We have some really good tooling to help you so that they don't tend to happen. We pretty much keep all of the code in Google data race free using dynamic analysis, a tool that does this. It's part of the standard toolkit that comes with Go. But I won't pretend that it wouldn't be nice to not have it by design rather than clean it up after the fact. But this is a compromise. We made this compromise deliberately. We know what we were doing, and it worked out really well. And conventions in the community, the understanding of orthogonality and the language design can help a lot here. And it turns out in practice, this is not a problem. Data races, they exist, but we fix them. They're not really a big deal. And the result is you get a really strong language out of this. And there's actually kind of a big thing here because you have threads you don't care about, stack management you don't care about, locking you don't care about. You can build real concurrent programs even if you're not very good at concurrency. You can understand what's going on the page really nicely. And so we've met our goal of being able to have fairly novice programmers build interesting concurrent programs that are robust and work really well. And it scales really well. There's also secondary support that's critical to making this work. There's a runtime, of course, that does dynamic scheduling and does the channel management and routine management and all that kind of stuff. There's a garbage collector, but there's only a garbage collector. There's no way to free memory other than letting the garbage collector get it for you. And there's 3 reasons for this. One is safety. You can argue that it's not the only thing you need for safety, but if there's garbage collection, you know that you're not going to have dangling pointers the way that they're dangerous. You can simplify resource management profoundly, which is critical in a concurrent program. When you're passing values around on channels, you don't want to have to worry about whose job it is to deallocate the thing when it's done, right? And also, perhaps most important of all, garbage collection makes the APIs so much simpler. When you're writing C++ code, half of your API is figuring out who owns what. And in Go, it's not an issue. You just write your code, and the garbage collector magically takes care of it. Obviously, I'm overstating. I exaggerate to clarify. But it works. So let me give you a demo. This is a complete Go program that doesn't show you any concurrency, but has a lot of it. It's a web server. Let me see if I can run it. What the hell, whatever. Okay, so here we go. This is running a file server. Let me pick a page here. And you can see I can whack around here. Okay, so this is all being served out of that program I just started from inside my slide deck, which is itself interesting. What happened when I hit that button to start this was this program was compiled, linked, and run right out of the slide deck on my machine, and then launched up, and then I'll do it again. It'll compile, link, and run it. It's running. And that's Apple yelling at me. That's their problem. But then I have a file server. Okay. Now, who cares, right? Anybody can implement browsers. That's easy, or browser web pages. But what's interesting here is that this is the complete program. This is the hello world of Go, if you like, right? And behind the covers in this sort of magic line here, obviously any library could make this happen, but there's actually a profound amount of concurrency going on in the library. So if you wanted, you could launch this on Google App Engine or something as your program, and it would work with thousands of concurrent clients talking to it at once with no further preparation. It would just work out of the box. And it's partly the library, but it's much more to do with the way the library builds on the language and its concurrent facilities to make it really easy to write large, scalable apps. If you hear people talk about the scalability issues with Node, the scalability issues around Ruby on Rails, this is our answer to them. Why have those issues at all? And so to come back to my earlier point, this is all about for coding at scale. There's a lot of stuff in Go that's designed for programming the large programs now. Packages and dependencies are really well designed and clean. They're very efficient. The language is statically typed. The syntax is clean and readable, designed for really easy tooling and IDE development. It's to focus on composition rather than inheritance as a type system. I can talk about types some other time. There's a very strict separation throughout the language between what the interface to your thing is and what the implementation of the thing is, which makes this kind of all really nice and composable. And there's an interesting error model that some people object to, but I think is really important. And for those of you who are actually interested in the details behind this slide, I gave a talk at Splash a year and a half ago, which covers all this in great detail. It's available as a video or as an article. And so to summarize, Go is orthogonal. The features are made to work well orthogonally, which is to say, if I take a method and a concurrent feature and stick them together, it just works. There's no funny rough edges when you try to combine features of Go. They're designed to work without any explanation. You don't have to look at the spec every time you combine two funny things to see what's going to happen. That makes the language small because you don't have to describe as much, and it's also free of unpleasant surprises. It's compact. The language spec, which is enough to implement it, because several people have done so, is about 50 pages. It only has 25 keywords. That's too many, but it's less than any other language I know except maybe Lisp. It's very readable, I claim. People tell me that it is readable, which makes it easy to read. It also means that it's easy to read someone else's program, not just my own. If it's easy to read, it's easy to learn. Many people have said they've literally learned it on a weekend and been productive the next day. It's actually pretty efficient. It compiles to native machine code. Our goal was to get within ballpark range of C. We knew we'd never be as good as C. But depending on your code, it can be as fast as C down to like half the speed. But that's pretty good for a language that's garbage collected and much more lightweight and fun to work in. The linkers are statically, the programs are statically linked, which deployers of web pages really like. The compilers are really fast, and the tools are really interesting, which is another thing I could talk about. And Go is very usable. I state this because it seems to be taking off. This is a graph from the trends graph from Google Trends And you can see that somewhere around here, does that show up? There's a key, there's a kink in the graph in mid-2012, which is when we standardized on Go 1.0 and said we weren't going to change anything anymore. We weren't going to break your code anymore. And all of a sudden it became something people could really use, and it's a very, very steeply rising curve. Both and the internal and external usage is pretty much the same shaped curve. And Go seems to be having an effect on the world. Concurrency has been around a long time. I didn't invent any of this. I don't claim to. But it seems that Go has taught programmers at large in the world that concurrency is something they can actually use in their programs and appreciate. And I really like that. I also like the fact that inside Google, the C++ concurrency model we're using now is pretty much directly what Go did. We showed how to do it well, and the C++ community inside Google has responded by doing something that makes really good sense for C++, but is still fundamentally the Go model, and I'm really happy with that. Last year, Rich Hickey implemented this thing called core.async for closure, which is explicitly modeled on Go. There's some others that aren't so public about their influences, but I know they're there, and that makes me feel good. Also, we're having a big effect on the open source culture, I think. This notion of the way the language is designed, the availability of concurrency, deployment, testing, the tooling infrastructure we've built around readability, seems to be having an effect on the language at large, and on the community at large. You see people asking for some of the Go secondary features, like the tool structure, to be wishing they're available in languages like Python, Ruby, and so on. So in conclusion, Go made concurrency easy, just the way Sawzall made concurrency easy, even for people who were relatively beginners, not as low level as Sawzall programmers, but pretty easy for people who'd never dealt with concurrency before. And first-class concurrency can, in fact, work very well within a procedural language, even though the concurrency programming experts would like not to think that sometimes, I believe. When you focus on the problem, which our problem is building Google servers, you end up with a language that may not be able to do everything that some other languages can do, but it might be really good for the particular problem you have. And that's an obvious lesson, but it's sometimes forgotten. And so in the big picture here, you can take big ideas like parallelism and concurrency, ideas that people are afraid of, and by presenting them the right way or hiding them completely, you can make them really useful to the community at large. And the trick is to keep the language easy and approachable so that the new idea you're bringing in just sort of works out by itself. You don't have to fuss for it. And one key point I want to make here is that language features, people tend to love to put features in their languages. We get feature requests literally every day for Go, and we reject almost all of them, and in fact, like 99.99% of them. Because features themselves are always useful. Otherwise, people wouldn't be proposing them. It's not whether they're useful or not. It's whether they're useful enough. Does a feature add enough, not only for itself, but does it make the rest of the language better? If a feature goes in and it doesn't make the rest of the language better, then there's no point in having it there, because it can live entirely outside the language. And that point is often lost by the people who design languages. And well, I won't single out any names like ECMAScript. That would be unfair. Sorry. Oh, did I say that? Did I say that out loud? Anyway, thank you very much for listening to this dilettante come in and talk to the community who know much more about this stuff than I do. Thank you very much. Yeah.
Sure. The switch or select statement that you showed, you said this is like the crux of a lot of the power. Can you give an example to kind of illustrate why that's true?
Well, I've tried not to give all the talks I've given before, right? So I've given a talk called Go Concurrency Patterns, and there's a guy named Samir Ajmani gave another one called Advanced Go Concurrency Patterns. They go into these in great detail. But the thing is that what select gives you is the control over a set of independently executing guys. It gives you it's like if you want to build a multiplexer, or you need to do shutdown, or you need to any kind of high-level programming of these independently executing things, you always end up expressing it as a select, often inside a loop, which is waiting for events to come in and control their management. So it's very easy to write simple stuff using Go routines and channels, but you can't implement a web server unless you end up having a select somewhere near the core that's doing the railway dispatching to get all the things to run on the rails. Does that make sense? But you might want to look at those talks if that actually interests you. Mm-hmm.
Yeah. In Sawzall, you hadn't. The point that was made earlier was you didn't mention concurrency at all, but handled it because it was deployed in a system that would handle that. So the definition of how the concurrency is being managed is in some batch language or some other place in terms of where it's being deployed. In Go, you're explicit within the program, which in some ways limits the way that you deploy it.
Yes. So the point is that in Sawzall, the parallelism, I would not call it concurrency, I would call it parallelism, was completely hidden, and that was deliberate. The parallelism was done by the system. The language just lived above it and let you control the system, and the language was severely restricted so that it could be parallelizable.
Was there a separate language was there a separate sort of batch definition language that said how many cores you would use and how many?
Yeah, but yes, there is such a configuration setup, but that's done by the cluster management code. It wasn't part of Sawzall per se. For Go, we needed more control than that model would let us give it. We couldn't hide the concurrency completely for the way we were thinking about it. I don't claim that that's not possible. It'd be interesting to try, and I've thought a lot about trying to make a web programming language where the concurrency is completely hidden, but the scalability is there. And I have some ideas, but I don't know if I'll ever get to play with them. You're making a valid point. It's implicit in this talk. You can hide it completely and get success. You can carefully expose it, and you can have success. What I claim you can't do is just lay out a library and say, woohoo, go for it, and expect it to be as successful as you'd like it to be. People are going to abuse it.
Do you use Go for the same type of jobs that you use Sawzall for?
Yes, we do. We use Go is actually partly the replacement for Sawzall. There's a much more around that ecosystem, but Go is the core computing engine for the new logs world. Yeah. Among lots of other things. Someone once said fairly recently, and I think correctly, if you look at a cat video on the web or a cat picture on the web, there's a Go server in there somewhere. Because so many content distribution networks and YouTube and stuff like that are using it now. Yeah, I'm not used to success. It's very strange. Yes?
So you mentioned some of the strengths of Go. What do you think are some of the weaknesses? Like, what kinds of programs would you not want to try to write?
We deliberately didn't worry about whether Go would be a good language for writing operating systems or real-time systems or embedded systems. The runtime is too big to be in a small computer. We did not want to compromise on having garbage collection as the only thing. So operating system things, you could do it, but I wouldn't recommend it. It's turned out to be much more useful, more general purpose than we intended it to be. But I still think those things it would not be a good choice for.
Is the Go compiler written in Go?
The Go compiler is not written in Go for another couple of months. We're in the process of rebooting it all in Go.